Introduction to HTTP Evolution. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into the evolution of HTTP, one of the most fundamental protocols that powers the modern web. When you type a URI in your browser or click a link, HTTP is the protocol facilitating the communication between your browser and web servers. Understanding the differences between HTTP/1.1, HTTP/2, and HTTP/3 is crucial for anyone working in web development, cloud infrastructure, or network engineering. The progression from HTTP/1.1 to HTTP/2 and then to HTTP/3 represents decades of innovation aimed at solving real-world performance problems. HTTP/1.1, released in 1997, served us well for nearly 2 decades, but the modern web's demands exposed significant limitations in its design. These limitations led to the development of HTTP/2 in 2015, which introduced revolutionary concepts like multiplexing and header compression. Most recently, HTTP/3 emerged as a radical reimagining that abandons TCP entirely in favor of QUIC, a protocol built on UDP. In this presentation, we will also explore 2 critical security concepts that intersect with HTTP protocols. First, we will examine HTTPS stripping attacks, a man-in-the-middle technique that downgrades secure connections to insecure ones, allowing attackers to intercept sensitive data. Second, we will understand application layer protocol negotiation, or ALPN, which enables clients and servers to negotiate which HTTP version to use during the TLS handshake, ensuring secure and efficient protocol selection. By the end of this presentation, you will understand not just the technical differences between these protocols, but also why these differences matter for website performance, security, and user experience. You will be equipped to make informed decisions about protocol support in your infrastructure and understand the security implications of each version. HTTP/1.1 Fundamentals. Let's begin our journey by understanding HTTP 1.1, the protocol that powered the web for nearly 20 years and continues to be widely supported today. HTTP 1.1 operates on a simple request-response model where each request from the client requires a separate response from the server. This simplicity made it easy to implement and debug, which contributed to its widespread adoption and longevity. The fundamental architecture of HTTP 1.1 is built on TCP, the Transmission Control Protocol. TCP provides reliable, ordered delivery of data between client and server. Every HTTP 1.1 connection begins with a TCP three-way handshake, where the client and server exchange SYN ACK, and ACK packets to establish the connection. This handshake ensures both parties are ready to communicate, but it also introduces latency before any actual HTTP data can be transmitted. One of the defining characteristics of HTTP/1.1 is its text-based format. HTTP headers and request lines are transmitted as human-readable ASCII text, which makes debugging with tools like Wireshark or TCP dump straightforward. You can literally read the HTTP conversation in a packet capture. However, this text-based format comes with overhead. Headers are verbose and repetitive, with common headers like user agent, accept, and cookie being sent with every single request, even when they haven't changed. HTTP/1.1 introduced persistent connections through the connection keep alive header, which was a significant improvement over HTTP/1.0. Instead of closing the TCP connection after each request-response pair, the connection could be reused for multiple requests. This eliminated the overhead of establishing new TCP connections for every resource. However, even with persistent connections, HTTP/1.1 suffers from head-of-line blocking, where requests must be processed sequentially on a single connection. If one request takes a long time to complete, all subsequent requests on that connection must wait. To work around head-of-line blocking, browsers implemented connection pooling, typically opening 6 parallel TCP connections per domain. This parallelism allowed multiple resources to be downloaded simultaneously, but it came at a cost. Each connection requires memory on both client and server, consumes port numbers, and goes through its own TCP handshake. This approach also wasn't scalable for modern web pages that might load hundreds of resources. The limitations of HTTP/1.1 became increasingly apparent as websites grew more complex, leading to the development of HTTP/2. HTTP/1.1 architecture and limitations. Looking at the architectural diagram, we can see how HTTP/1.1 handles multiple resource requests. The client establishes a TCP connection with the server, and then requests flow sequentially down this connection. Each request must wait for the previous response to complete before the next request can be processed on that connection. This visualizes the head-of-line blocking problem. Notice in the diagram how the client opens multiple TCP connections simultaneously. Modern browsers typically use 6 connections per domain, which you can see represented in the parallel streams. Each connection goes through its own TCP handshake, shown as the SYN ACK sequence at the beginning. This handshake happens every time a new connection is established, adding latency before any actual HTTP data can flow. The resource loading pattern shows how files are downloaded. For connection 1, perhaps we're downloading the HTML file. For connection 2, the CSS stylesheet. For connection 3, a JavaScript file, and so on. This parallelism helps, but it's inefficient. Each connection maintains its own TCP congestion control state, flow control windows, and buffers. The server must track all these connections separately, consuming memory and processing resources. What is particularly problematic is when you have more resources to load than available connections. If your web page needs 50 resources, but you only have 6 connections, those resources must queue up and wait. The browser implements sophisticated prioritization logic to determine which resources to fetch first, but ultimately it is constrained by the limited number of connections. This queuing adds latency and slows down page load times. Another issue not immediately visible in the diagram is header overhead. Every request sends the same headers repeatedly. If you have a user agent header that is 200 bytes and you make 50 requests, you have sent bytes of redundant header data. Cookies can make this even worse, with some cookies being several kilobytes in size and being sent with every single request to the domain. This redundant header transmission wastes bandwidth and adds latency, especially on slower network connections. The diagram also illustrates why connection pooling has limits. Operating systems have limits on the number of file descriptors and ephemeral ports available. Servers have limits on the number of concurrent connections they can handle. When you multiply these limitations by thousands or millions of clients, you can see why HTTP/1.1's architecture doesn't scale well for modern web applications. These limitations motivated the development of HTTP/2, which we will explore in the next slides. HTTP/2 revolution. HTTP/2 represents a fundamental reimagining of how HTTP works, while maintaining complete compatibility with HTTP/1.1 semantics. Released in 2015, HTTP/2 was based on Google's SPDY protocol and addressed the major performance bottlenecks of HTTP/1.1. The most revolutionary change is the introduction of binary framing, replacing HTTP/1.1's text-based protocol with a more efficient binary format. At the heart of HTTP/2 is the concept of multiplexing. Instead of sending requests sequentially on separate connections, HTTP/2 allows multiple requests and responses to be interleaved on a single TCP connection. This is achieved through the binary framing layer, which breaks down HTTP messages into small frames. Each frame is tagged with a stream identifier, allowing multiple streams to share the same connection without interfering with each other. This completely eliminates the need for browsers to open multiple connections per domain. The binary framing layer divides communication into frames and streams. A stream is a bidirectional flow of frames within a single HTTP/2 connection, representing one request-response exchange. Frames are the smallest unit of communication, carrying different types of data like headers, data, priority, or settings. Because frames from different streams can be interleaved, HTTP/2 can start sending the response for request B while still receiving the request for A, something impossible in HTTP/1.1. Another major innovation is HPACK header compression. HTTP/2 maintains a header table on both client and server, tracking previously sent headers. When a header is sent that matches one in the table, only a reference to the table entry is transmitted instead of the full header value. For headers that haven't been seen before, HTTP/2 uses Huffman encoding to compress the header before transmission. This dramatically reduces the overhead of header transmission, particularly beneficial for requests with large cookies or custom headers. HTTP/2 also introduces server push, a feature that allows servers to proactively send resources to the client before they are requested. If a server knows that a client requesting index.html will also need style.css and script.js, it can push those resources immediately. This eliminates round trips and can significantly improve page load times. However, server push requires careful implementation to avoid pushing resources the client already has cached. Stream prioritization is another sophisticated feature in HTTP2. Clients can assign weights and dependencies to streams, allowing them to communicate to the server which resources are most important. For example, CSS files might be prioritized over images since CSS is needed to render the page. This prioritization helps ensure that critical resources are delivered first, improving the perceived performance of the application. Despite these improvements, HTTP2 still relies on TCP, which means it inherits TCP's limitations, particularly head-of-line blocking at the transport layer. HTTP/2 multiplexing architecture. This diagram illustrates the revolutionary multiplexing capability of HTTP/2. Unlike HTTP/1.1, which required multiple TCP connections, HTTP/2 uses a single TCP connection to handle all communication between client and server. This connection carries multiple logical streams, each representing a separate request-response exchange. In the diagram, you can see Stream 1, Stream 2, and Stream 3 all sharing the same underlying TCP connection. Each stream is independent and can be processed concurrently. The binary framing layer breaks down the HTTP messages into small frames, and these frames are multiplexed onto the connection. Notice how frames from different streams can be interleaved. A data frame from Stream 1 might be followed by a headers frame from Stream 2, then another data frame from Stream 1, and so on. This interleaving is what eliminates head-of-line blocking at the HTTP layer. The frame structure is crucial to understanding HTTP/2's efficiency. Each frame has a header that includes the stream identifier, frame type, flags, and length. The stream identifier allows the receiver to reassemble frames back into their respective streams. The frame type indicates whether it is carrying headers, data, priority information, or control information. This binary format is much more efficient to parse than HTTP/1.1's text-based format, and enables the multiplexing functionality. Looking at the flow in the diagram, you can see how multiple resources are requested and received simultaneously over a single connection. There is no waiting for one request to complete before starting another. The client can send multiple headers frames to initiate several streams, and the server can respond to them in any order based on resource availability and stream priorities. This asynchronous processing is a key performance benefit of HTTP/2. However, it is important to understand that while HTTP/2 eliminates head-of-line blocking at the application layer, the underlying TCP connection can still experience head-of-line blocking at the transport layer. If a TCP packet is lost, TCP's reliability mechanism requires that packet to be retransmitted and processed in order before subsequent data can be delivered to the application. This means all streams on the connection must wait for that single lost packet to be recovered, even if those streams do not depend on that data. This TCP-level head-of-line blocking becomes particularly problematic on high-latency or lossy networks. The diagram also shows how HTTP/2 maintains persistent connections. Unlike HTTP/1.1, where connections could be closed and reopened, HTTP/2 connections are typically long-lived, staying open for the duration of the browsing session. This eliminates the overhead of repeated TCP handshakes and TLS handshakes, resulting in faster subsequent requests. The connection can handle hundreds or even thousands of streams over its lifetime, making it extremely efficient for modern web applications with many resources. HTTP/2 features comparison. This comparison table highlights the key technical differences between HTTP/1.1 and HTTP/2, helping us understand the specific improvements HTTP/2 brings to the table. The first row shows the protocol format, where HTTP/1.1 uses a text-based format with human-readable headers and request lines, while HTTP/2 employs a binary framing layer. The binary format is more compact and efficient to parse, though it makes debugging slightly more challenging since you can't just read the protocol in plain text anymore. The multiplexing capability is perhaps the most significant difference. HTTP/1.1 sequential processing means that requests must be handled one at a time on each connection, leading to head-of-line blocking. HTTP/2's multiplexing allows multiple requests and responses to be in flight simultaneously on a single connection, with frames from different streams being interleaved. This single capability eliminates the need for browsers to open multiple connections per domain, reducing complexity and resource consumption on both client and server. Header compression is another major improvement. In HTTP 1.1, headers are sent in full with every request, leading to significant redundancy, especially for headers like user agent and cookie that rarely change. HTTP 2's HPACK compression maintains a dynamic table of previously sent headers and uses references to these table entries instead of retransmitting the full header values. Additionally, HPACK applies Huffman encoding to new header values, further reducing the size. This compression can reduce header overhead by 80% or more in typical scenarios. The connection usage row reveals a fundamental architectural difference. HTTP/1.1 relies on multiple connections per domain, typically 6 in modern browsers. Each connection requires its own TCP handshake, TLS handshake if using HTTPS, and maintains separate TCP state. HTTP/2 consolidates all communication onto a single connection, which reduces latency, simplifies connection management, and reduces resource consumption. This single connection handles all the streams, priorities, and flow control in a coordinated manner. Server push is a unique HTTP/2 feature with no equivalent in HTTP/1.1. In HTTP/1.1, the client must request each resource explicitly, leading to multiple round trips as the client discovers what resources are needed. HTTP/2 allows the server to proactively push resources to the client that it knows will be needed. For example, when the client requests an HTML page, The server can immediately push the associated CSS and JavaScript files without waiting for the client to parse the HTML and request them. This can significantly reduce page load times, though it requires careful implementation to avoid pushing resources the client already has cached. Finally, stream prioritization in HTTP/2 allows clients to communicate the importance and dependencies of different streams. The client can specify that stream A depends on stream B completing first, or that stream C should receive more bandwidth than stream D. This prioritization information helps servers allocate resources effectively, ensuring critical resources like CSS and JavaScript are delivered before less important resources like images. HTTP/1.1 has no such mechanism, with browsers relying on connection-level prioritization by controlling which resources they request on which connections, a much cruder approach. HTTP/3 and QUIC introduction. HTTP/3 represents the most radical evolution of HTTP yet, completely abandoning TCP in favor of QUIC, a transport protocol built on UDP. This might seem surprising since UDP is typically associated with unreliable, connectionless communication, while HTTP requires reliability. However, QUIC implements its own reliability mechanisms on top of UDP, combining the benefits of TCP's reliability with improvements that address TCP's fundamental limitations. The motivation for HTTP/3 stems from TCP's head-of-line blocking problem at the transport layer. Even though HTTP/2 eliminated head-of-line blocking at the application layer through multiplexing, the underlying TCP connection could still block all streams if a single packet was lost. TCP's ordered delivery guarantee means that if packet 100 is lost, packets 101, 102, and beyond cannot be delivered to the application until packet 100 is retransmitted and received, even if those later packets arrived successfully and belong to completely different HTTP/2 streams. QUIC solves this by implementing streams natively at the transport layer. Each QUIC stream has its own sequence space and flow control. If a packet belonging to stream 1 is lost, only stream 1 is blocked while the retransmission occurs. Streams 2, 3, and beyond can continue delivering data to the application without waiting. This true multiplexing without head-of-line blocking significantly improves performance on networks with packet loss, which includes most mobile networks and many Wi-Fi connections. Another major benefit of QUIC is its integration with TLS 1.3. In TCP-based HTTP/2, you have separate handshakes for TCP and TLS, requiring multiple round trips before any application data can be sent. The client sends a TCP SYN, receives a SYN ACK, sends an ACK, then starts the TLS handshake with client hello, receives server hello, and so on. With QUIC, the transport handshake and TLS handshake are combined into a single exchange. This reduces connection establishment time from 2 to 3 round trips down to 1 round trip for new connections, and 0 round trips for resumed connections. Connection migration is another innovative feature of QUIC. Traditional TCP connections are identified by a 4-tuple of source IP, source port, destination IP, and destination port. If any of these change, the connection is broken. This is problematic for mobile devices that frequently switch between Wi-Fi and cellular networks, or between different cell towers. QUIC uses connection IDs instead of the 4-tuple, allowing a connection to survive network changes. When your phone switches from Wi-Fi to cellular, your QUIC connections continue seamlessly without interruption or re-establishment. QUIC also benefits from being implemented in user space rather than kernel space like TCP. TCP is part of the operating system kernel, and updating TCP requires OS updates, which are slow to deploy and adopt. QUIC is implemented in application libraries and can be updated much more quickly. This allows for rapid iteration and improvement of the protocol. When a QUIC implementation discovers a bug or wants to add a new feature, it can be deployed in weeks rather than years. This flexibility is crucial for a protocol designed for the rapidly evolving web. HTTP/3 architecture with QUIC. This architectural diagram shows how HTTP/3 structures its communication stack, which is fundamentally different from both HTTP/1.1 and HTTP/2. At the top, we have the HTTP/3 layer, which uses the same HTTP semantics as previous versions. Methods, headers, status codes, and message body concepts remain unchanged. This ensures applications can migrate to HTTP/3 without requiring extensive code changes. The familiar get, post, put, delete methods work exactly as they did before. Below the HTTP/3 layer is the QUIC transport protocol, which is where the revolutionary changes happen. QUIC implements multiple independent streams, shown as Stream 1, Stream 2, and Stream 3 in the diagram. Each stream provides reliable, ordered delivery of data, similar to what TCP provides, but streams are isolated from each other. If Stream 1 experiences packet loss, it doesn't affect the delivery of data in Stream 2 or Stream 3. This stream-level independence eliminates the transport layer head of line blocking that plagued HTTP/2 over TCP. QUIC also integrates encryption deeply into its design. Unlike TCP, where TLS is a separate layer negotiated after the TCP connection is established, QUIC includes TLS 1.3 as an integral part of the protocol. The QUIC handshake and TLS handshake are combined, reducing connection establishment latency. Additionally, QUIC encrypts almost all packet headers, including the packet number, providing better privacy than TCP. Only the connection ID and a few flags are transmitted in cleartext. At the bottom of the stack is UDP, the User Datagram Protocol. UDP is connectionless and provides no reliability, ordering, or congestion control. It simply sends packets from source to destination without guarantees. This might seem like a step backward, but it is actually liberating. By building on UDP, QUIC avoids the ossification problems of TCP network middleboxes like firewalls, NAT devices, and proxies. Do not try to optimize or modify QUIC packets the way they do with TCP, giving QUIC more flexibility. UDP also allows QUIC to be implemented in user space, enabling faster deployment of protocol improvements. The diagram shows how QUIC implements its own congestion control, loss detection, and connection establishment mechanisms on top of UDP. QUIC's congestion control is pluggable, allowing different algorithms to be used based on network conditions. Loss detection in QUIC is more sophisticated than TCPS, using mechanisms like packet number spaces and ACK frames with timestamp information. The connection establishment combines the transport and cryptographic handshakes into a single 1 RTT or even 0 RTT exchange for resumed connections. One important aspect shown in the diagram is the connection ID. Unlike TCP, which identifies connections by the 4-tuple of IP addresses and ports, QUIC uses explicit connection IDs negotiated during the handshake. These connection IDs allow the connection to survive network changes. If a mobile client switches from Wi-Fi to cellular, changing its IP address, the QUIC connection continues using the same connection ID. The server recognizes the connection despite the IP change and continues the communication seamlessly. This connection migration capability is essential for the mobile-first modern web. HTTP/1.1, HTTP/2, and HTTP/3 comparison. This comprehensive comparison table helps us see the evolution from HTTP/1.1 through HTTP/2 to HTTP/3 across several critical dimensions. Starting with the transport protocol, HTTP/1.1 and HTTP/2 both use TCP, the reliable transport protocol that has powered the Internet for decades. HTTP/3 breaks from this tradition by using QUIC over UDP, which might seem risky but provides significant benefits as we have discussed. This transport change is the most fundamental difference and drives many of the other improvements in HTTP/3. Looking at the multiplexing row, we see a clear progression. HTTP/1.1 has no multiplexing. This requires sequential request processing on each connection and leads browsers to open multiple connections per domain. HTTP/2 introduced application layer multiplexing, allowing multiple streams on a single TCP connection, but these streams could still be blocked by TCP-level packet loss. HTTP/3 achieves true independent streams at the transport layer, with QUIC streams being completely isolated from each other. This means packet loss in one stream only affects that stream, not all streams on the connection. The head-of-line blocking comparison is particularly revealing. HTTP/1.1 suffers from application-level head-of-line blocking where one slow request blocks others on the same connection. HTTP/2 eliminated application-level blocking through multiplexing but introduced transport-level blocking because all HTTP/2 streams share a single TCP connection. If any TCP segment is lost, all streams must wait for its retransmission due to TCP's ordered delivery requirement. HTTP/3 finally eliminates head-of-line blocking entirely by implementing streams at the transport layer in QUIC, where each stream has independent loss recovery. Connection establishment is another area of significant improvement. HTTP/1.1 requires a TCP handshake and, if using HTTPS, a separate TLS handshake, totaling 2 to 3 round trips before application data can be sent. HTTP/2 over TLS has the same requirement since it uses TCP with TLS layered on top. HTTP/3 combines the transport and cryptographic handshakes into a single exchange, achieving 1 RTT for new connections and 0 RTT for resumed connections. This dramatically reduces latency, particularly beneficial for short-lived connections or users with high latency connections. The header compression comparison shows incremental improvement. HTTP/1.1 sends headers as uncompressed text, leading to significant overhead, especially with large cookies or many custom headers. HTTP/2 introduced HPACK compression, which uses a static and dynamic table to avoid retransmitting redundant headers, plus Huffman encoding for new values. HTTP/3 uses QPACK, an evolution of HPACK designed for QUIC's out-of-order delivery model. QPACK provides similar compression benefits to HPACK but works correctly even when packets arrive out of order, which can happen more frequently with QUIC. Finally, connection migration shows where HTTP/3 truly shines for mobile users. HTTP/1.1 and HTTP/2 both use TCP, which identifies connections by IP address and port. When a mobile device switches from Wi-Fi to cellular, its IP address changes, breaking all TCP connections and requiring re-establishment. This causes noticeable interruptions in video streaming, file downloads, and web browsing. HTTP/3's QUIC uses connection IDs independent of network addresses, allowing connections to survive IP changes seamlessly. When your phone switches networks, your HTTP/3 connections continue without interruption, providing a much smoother user experience for mobile users who frequently move between networks. HTTPS stripping attacks. Now that we understand the evolution of HTTP protocols, let's examine a critical security threat that affects all versions: HTTPS stripping attacks. Despite the widespread adoption of HTTPS, which encrypts communication between clients and servers, many users still begin their web browsing by typing domain names without the protocol prefix. When you type example.com in your browser, It typically makes an initial HTTP request before being redirected to HTTPS. This initial unencrypted request creates a vulnerability window that attackers can exploit. An HTTPS stripping attack is a form of man-in-the-middle attack where an attacker intercepts the communication between a client and server and downgrades the connection from HTTPS to HTTP. The attack works by positioning the attacker between the client and the legitimate server, typically on the same local network like a coffee shop Wi-Fi or compromised router. The attacker intercepts the client's initial HTTP request and forwards it to the server over HTTPS, then intercepts the server's HTTPS redirect response and strips the security layer, sending the client an HTTP response instead. The clever part of this attack is that the client believes it is communicating over HTTP with the legitimate server, while the attacker is actually proxying the communication over HTTPS to the real server. From the client's perspective, everything looks normal except the lack of the padlock icon in the browser. Many users do not notice or understand the significance of the missing padlock, so they continue entering sensitive information like passwords and credit card numbers. The attacker can read all this data in cleartext since the connection between client and attacker is unencrypted. Tools like Secure Sockets Layer Strip, developed by security researcher Moxie Marlinspike, automate this attack. Secure Sockets Layer Strip sits on the network and watches for HTTP traffic. When it sees an HTTP request that would normally trigger an HTTPS redirect, it intercepts the redirect and modifies it to keep the connection as HTTP. It also modifies any HTTPS links in the HTML content to HTTP links, ensuring that future requests also remain unencrypted. This allows the attacker to maintain the downgraded connection for the entire browsing session. The attack is particularly effective because it exploits user behavior and browser defaults. Most users do not manually type https:// before domain names, and browsers historically defaulted to HTTP for bare domain entries. Even today, while browsers may try to upgrade to HTTPS, the initial request is often HTTP. Additionally, many websites still redirect from HTTP to HTTPS rather than rejecting HTTP requests entirely, providing the opportunity for the attack to succeed. The attack also works against HTTP/2 and HTTP/3, as the vulnerability lies in the initial protocol negotiation, rather than the specific HTTP version being used. Defending against HTTPS stripping requires multiple approaches. HTTP Strict Transport Security, or HSTS, is a mechanism where servers tell browsers to only communicate over HTTPS for a specified duration. Once a browser receives an HSTS header, it will refuse to make HTTP requests to that domain for the specified time period, even if the user types HTTP explicitly. HSTS preload lists extend this protection to the first connection by including domains in browsers' built-in HSTS lists. We'll explore these defenses in detail in upcoming slides, along with how ALPN helps ensure secure protocol negotiation. HTTPS stripping attack mechanics. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. To truly understand how to defend against HTTPS stripping attacks, we need to examine the detailed mechanics of how these attacks work. The attack leverages a fundamental vulnerability in how users interact with websites. When a user types a domain name like banking.com into their browser's address bar, they typically don't specify the protocol. The browser must decide whether to use HTTP or HTTPS for the initial request. Historically, browsers defaulted to HTTP, creating an attack window. The attack requires the attacker to be positioned as a man in the middle, which is surprisingly easy on many networks. On a public Wi-Fi network at a coffee shop, airport, or hotel, an attacker can use ARP spoofing to position themselves between victims and the router. ARP spoofing works by sending falsified ARP messages on the local network, associating the attacker's MAC address with the IP address of the router. This causes all traffic from victims to flow through the attacker's machine before reaching the actual router. Once positioned as a man in the middle, the attacker runs tools like SSL strip or MITM proxy configured for HTTPS stripping. These tools intercept HTTP traffic and watch for specific patterns. When the attacker sees an HTTP request to a domain, they forward that request to the real server using HTTPS, establishing a secure connection with the server. The server responds with an HTTPS redirect, typically a 301 or 302 status code with a location header pointing to the HTTPS version of the site. Here's where the attack happens. Instead of forwarding the HTTPS redirect to the client, the attacker strips the security. They change the redirect to point to an HTTP URL, or they simply fetch the HTTPS content and serve it to the client over HTTP. The attacker also modifies all links in the HTML content, changing any HTTPS links to HTTP links. This ensures that when the user clicks links or submits forms, those requests also go over HTTP, maintaining the attack throughout the browsing session. From the client's perspective, the website loads normally. The only indication that something is wrong is the absence of the padlock icon in the browser's address bar and the presence of HTTP instead of HTTPS in the URL. Many users don't notice or understand these indicators, especially on mobile devices where the URL bar is condensed. The user continues interacting with the site, entering passwords, credit card numbers, and other sensitive information, all of which the attacker can read in clear text. The attack is effective because it does not require breaking any cryptography. The attacker is not decrypting HTTPS traffic or cracking certificates. Instead, they are exploiting user behavior and browser defaults to prevent HTTPS from being used in the first place. The connection between the attacker and the real server is properly encrypted with HTTPS, so the server does not detect anything suspicious. Only the connection between the client and attacker is unencrypted, and that is where the data theft occurs. This attack demonstrates why defense mechanisms like HSTS are so critical for web security. HTTP Strict Transport Security HSTS. HTTP Strict Transport Security, commonly known as HSTS, serves as the primary defense mechanism against HTTPS stripping attacks. HSTS is a web security policy mechanism defined in RFC 6797, allowing web servers to declare that browsers should only interact with them using secure HTTPS connections, and never over insecure HTTP. Once a browser receives an HSTS policy from a server, it will refuse to make HTTP connections to that domain for a specified duration, even if the user explicitly types http:// in the address bar. The HSTS policy is communicated through an HTTP response header called Strict Transport Security. This header includes a max age directive that specifies how long the browser should remember the policy, measured in seconds. A typical HSTS header might look like Strict Transport Security max age equals beginning with 31 ending with 00, which instructs the browser to enforce HTTPS only access for 1 year. During this period, the browser will automatically upgrade any HTTP requests to HTTPS before sending them, preventing HTTPS stripping attacks. HSTS also supports the Include Subdomains directive, which extends the HTTPS-only policy to all subdomains of the domain. For example, if example.com sets an HSTS policy with include subdomains, the policy applies to www.example.com, api.example.com, admin.example.com, and all other subdomains. This is important because attackers might try to exploit subdomains that do not enforce HTTPS to establish an attack vector. However, the include subdomains directive must be used carefully, as it requires all subdomains to properly support HTTPS. The preload directive is another important component of HSTS when a domain includes preload in its HSTS header and submits the domain to the HSTS preload list maintained by browser vendors. The domain is included in a hard-coded list built into browsers. This means that even on the very first connection to the domain, before the browser has ever received an HSTS header from the server, the browser will enforce HTTPS-only access. This eliminates the trust on first use problem, where the initial connection is vulnerable to HTTPS stripping. HSTS configuration in headers. Let's look at the practical implementation of HSTS through server configuration. The code example shows how to configure the strict transport security header in Nginx, one of the most popular web servers. The header is added to the server block that handles HTTPS connections on port 443. HSTS preload list. The HSTS preload list is a powerful mechanism that eliminates the trust on first-use vulnerability inherent in standard HSTS deployment. With regular HSTS, a browser only learns about the HSTS policy after making at least one successful HTTPS connection to the domain and receiving the strict transport security header. HSTS enforcement flow. This diagram illustrates how HSTS enforcement works in a browser after the browser has received and stored an HSTS policy from a domain. Understanding this flow is crucial for grasping how HSTS protects against HTTPS stripping attacks. The process begins when a user attempts to access a website, either by typing a URL, clicking a link, or submitting a form. Let's walk through each step of this enforcement mechanism. At the top of the diagram, we see the initial user action where someone types example.com in the browser's address bar. This is the typical way users access websites, without specifying the protocol. In a non-HSTS scenario, the browser would default to HTTP and send an HTTP request, creating the vulnerability window for HTTPS stripping attacks. However, with HSTS enforcement active, the browser follows a different path. The first decision point is whether the browser has an HSTS policy cached for this domain. When a browser receives an HSTS header from a server, it stores that policy in a local database along with the domain name, the max age duration, and whether include subdomains is set. Before making any request to a domain, the browser checks this database. If an HSTS policy exists and hasn't expired, the browser knows it must use HTTPS. If no policy exists, or if the policy has expired past its max age, the browser proceeds with a normal HTTP request. When HSTS policy is present and valid, the browser automatically upgrades the request to HTTPS. This happens entirely on the client side, before any network communication occurs. Even if the user explicitly typed http://example.com or clicked on an HTTP link, the browser changes the URL to https://example.com internally. This automatic upgrade is what prevents HTTPS stripping attacks. The attacker never sees an HTTP request because the browser never sends one. The request goes directly to the server over HTTPS. The diagram shows the HTTPS request being sent to the server and the server responding. If the HTTPS connection succeeds, the page loads normally and the user sees the padlock icon, indicating a secure connection. The response includes an updated HSTS header that refreshes the policy's expiration time. Each time the browser successfully connects to the domain over HTTPS and receives an HSTS header, it resets the max age timer, ensuring the policy remains active for active users. Application Layer Protocol Negotiation, ALPN. Application Layer Protocol Negotiation, or ALPN, is a TLS extension defined in RFC 7301 that allows clients and servers to negotiate which application layer protocol to use during the TLS handshake. In the context of HTTP, ALPN is how browsers and servers agree on whether to use HTTP/1.1, HTTP/2, or HTTP/3. This negotiation happens securely within the encrypted TLS handshake, preventing protocol downgrade attacks and ensuring both parties agree on the protocol before any application data is transmitted. Before ALPN, protocol negotiation was more complicated and less secure. HTTP/1.1 was the default, and to use HTTP/2, an additional mechanism called Next Protocol Negotiation, or NPN, was employed. NPN had security and design issues, and it was not standardized. ALPN replaced NPN with a better design where the client announces its supported protocols in the client hello message, and the server selects one and announces its choice in the server hello message. This selection happens before encryption keys are established, but the handshake itself is integrity protected, preventing tampering. The ALPN extension in the client hello includes a list of protocol identifiers that the client supports, in order of preference. For HTTP, these identifiers include H2 for HTTP/2 over TLS, HTTP/1.1 for HTTP/1.1 over TLS, and H3 for HTTP/3 over QUIC. The client lists these in the order it prefers to use them. For example, a modern browser might list H2, HTTP/1.1, indicating it prefers HTTP/2 but can fall back to HTTP/1.1 if the server doesn't support HTTP/2. The server receives the client hello with the ALPN extension and examines the list of protocols. The server selects exactly one protocol from the client's list that the server also supports, typically choosing the first match in the client's preference order. The server includes this selected protocol in its server hello response in the ALPN extension. If the server does not support any of the protocols the client listed, the server can either refuse the connection or choose to omit the ALPN extension and fall back to HTTP/1.1 as a default. Once both client and server have agreed on the protocol through ALPN, they proceed with the rest of the TLS handshake and then begin application layer communication using the negotiated protocol. If HTTP/2 was negotiated, the client and server will exchange HTTP/2 frames. If HTTP/1.1 was negotiated, they will exchange HTTP/1.1 requests and responses. This negotiation is efficient because it happens during the handshake that must occur anyway for HTTPS, adding minimal overhead compared to the alternative of trying different protocols through trial and error. ALPN is particularly important for HTTP/3 and QUIC since HTTP/3 runs over UDP rather than TCP. There's no TCP connection to carry negotiation information. Instead, the client discovers HTTP/3 support through the alt-SBC header sent by the server in HTTP/1.1 or HTTP/2 responses, or through DNS HTTPS records. Once the client knows the server supports HTTP/3, it can initiate a QUIC connection. Within the QUIC handshake, which includes TLS 1.3, ALPN negotiation happens to confirm HTTP/3. The protocol identifier for HTTP/3 is H3, and this negotiation ensures both parties agree to use HTTP/3 over the QUIC connection. ALPN negotiation process. This sequence diagram illustrates the detailed ALPN negotiation process during a TLS handshake between a client and server. The diagram shows how protocol selection happens early in the connection establishment, before any application data is exchanged. Understanding this flow is essential for anyone working with modern HTTP implementations or debugging protocol negotiation issues. The process begins with the client sending a client hello message. This is the first message in the TLS handshake, and it contains various information including the TLS versions the client supports, cipher suites, and extensions. The ALPN extension is included in this client hello message, carrying a list of application protocols the client supports. In our example, the client sends H2 and HTTP/1.1, indicating it supports both HTTP/2 and HTTP/1.1, with HTTP/2 being preferred as it is listed first. The server receives the client hello and processes it. The server examines its own capabilities and compares them with the client's supported protocols listed in the ALPN extension. The server should select the first protocol in the client's list that the server also supports, respecting the client's preference order. In this example, the server supports HTTP/2, so it selects H2 as the protocol to use. If the server didn't support HTTP/2, it would select HTTP/1.1 instead. The server responds with a server hello message, which includes its selection in the ALPN extension. The ALPN extension in the server hello contains the single protocol ID the server has chosen. In our example, the server responds with H2, indicating that HTTP/2 will be used for this connection. This selection is final and binding for the connection. The client and server are now committed to using HTTP/2 for all application layer communication on this TLS connection. The rest of the TLS handshake continues with the server sending its certificate, the server hello done message, and then the client and server complete the key exchange. Once the handshake is finished, both parties have established encryption keys and agreed on HTTP/2 as the application protocol. At this point, the application data flow begins, but now it uses HTTP/2 framing instead of HTTP/1.1 text protocol. The client might start by sending an HTTP/2 settings frame, followed by headers frames for requests. This negotiation is secure because it happens within the TLS handshake, which has integrity protection. An attacker positioned as a man in the middle cannot modify the ALPN extension to force a protocol downgrade without being detected. If an attacker tried to change the client's ALPN list from H2, HTTP/1.1 to just HTTP/1.1 to force HTTP/1.1 usage, the TLS handshake would fail because the handshake messages include message authentication codes that would detect the tampering. This protection ensures that the protocol negotiation is secure and prevents downgrade attacks. The diagram also illustrates the efficiency of ALPN protocol negotiation adds no extra round trips to the connection establishment. The ALPN information is carried in the client hello and server hello messages that are already part of the TLS handshake. This is much more efficient than older approaches where the client might have to try connecting with HTTP/2, fail, and then retry with HTTP/1.1. ALPN allows the right protocol to be selected on the first try, reducing latency and improving the user experience. HTTP/3 discovery and ALPN. HTTP/3 presents a unique challenge for protocol discovery and negotiation because it operates over QUIC and UDP rather than TCP. A client cannot simply attempt an HTTP/3 connection to any server because UDP port 443 might not be open, QUIC might not be supported, or the server might not support HTTP/3 at all. The client needs a way to discover that HTTP/3 is available before attempting to use it. This is where the Alt-SVC header and ALPN work together to enable HTTP/3 adoption. The Alt-SVC header, which stands for Alternative Service, is an HTTP header that servers send to inform clients about alternative protocols and endpoints for accessing the same resource. When a server supports HTTP/3, it can send an alt-SVC header in its HTTP/1.1 or HTTP/2 responses, telling the client that HTTP/3 is available. The header might look like alt-SVCH3 equals :443. This tells the client that HTTP/3, identified by the H3 protocol identifier, is available on the same host at UDP port 443. When a browser receives an alt service header advertising HTTP/3 support, it caches this information. On subsequent requests to that origin, the browser can choose to use HTTP/3 instead of HTTP/1.1 or HTTP/2. The browser initiates a QUIC connection to the server on the specified UDP port. This QUIC connection includes the TLS 1.3 handshake, and within that handshake, ALPN negotiation occurs to confirm HTTP/3. The client includes H3 in its list of supported protocols in the ALPN extension, and the server confirms by selecting H3. This discovery mechanism creates a graceful upgrade path. Clients that do not support HTTP/3 simply ignore the alt-SVC header and continue using HTTP/1.1 or HTTP/2. Clients that do support HTTP/3 can opportunistically upgrade to HTTP/3 based on the alt-SVC advertisement. The initial connection still uses TCP-based HTTP, ensuring compatibility, but subsequent connections can use the more efficient HTTP/3. This approach allows HTTP/3 deployment without breaking existing clients. DNS-based discovery is another mechanism being developed for HTTP3. The HTTPS DNS record type allows servers to advertise HTTP3 support in DNS responses. When a client performs a DNS lookup for a domain, it can receive information about supported protocols, including HTTP3. This allows the client to know about HTTP3 support before making the first HTTP request, potentially allowing the very first connection to use HTTP3. However, DNS-based discovery is not yet as widely deployed as alt-service header-based discovery. Once an HTTP/3 connection is established, ALPN within the QUIC handshake ensures both parties agree on using HTTP/3. The ALPN negotiation in QUIC works the same way as in TLS over TCP, with the client listing supported protocols and the server selecting one. For HTTP/3, the protocol identifier is H3, and this must be successfully negotiated for HTTP/3 communication to proceed. If ALPN negotiation fails or indicates a different protocol, the client would fall back to HTTP/2 or HTTP/1.1 over TCP. This multi-layered approach with alt-service discovery, QUIC connection establishment, and ALPN negotiation ensures robust and secure HTTP/3 deployment. Protocol selection with alt-SVC. This diagram illustrates the complete HTTP/3 discovery and connection process using the alt-SVC header mechanism. The flow shows how a client transitions from HTTP/1.1 or HTTP/2 to HTTP/3 across multiple requests. This process demonstrates the backward compatible design of HTTP/3 deployment, ensuring that existing clients continue to work while new clients can take advantage of HTTP/3's benefits. The process begins with an initial HTTP/2 request from the client to the server over TCP. This might be the very first time the client is connecting to this server, or it might be a client that doesn't yet know that HTTP/3 is available. The request is a normal HTTP/2 request, sent over a TLS encrypted TCP connection established on port 443. The server receives and processes this request normally, generating an HTTP/2 response. In the server's HTTP/2 response, it includes an Alt-SBC header advertising HTTP/3 availability. The header specifies H3 equals :443, MA equals 3600, which tells the client that HTTP/3 is available on the same host at UDP port 443, and this information should be cached for 3600 seconds, or 1 hour. The MA parameter stands for max age and works similarly to cache control headers. The client receives this response along with the Alt-SBC header and processes both the response data and the protocol advertisement. The client stores the Alt-SBC information in its cache, associating it with this origin, which is the combination of scheme, host, and port. Now, for the next hour, the client knows it can attempt to use HTTP/3 when connecting to this server. This caching is important. It means the discovery process only needs to happen once. Subsequent connections can then immediately attempt HTTP/3 without first requiring another HTTP/2 connection. On the next request to the same origin, shown in the diagram as happening some time later, the client consults its alt service cache. It finds the cached information indicating HTTP/3 is available, so it decides to use HTTP/3 for this request. The client initiates a QUIC connection to the server on UDP port 443. This QUIC connection establishment includes the TLS 1.3 handshake with ALPN negotiation, where the client and server agree to use H3 for HTTP/3. Once the QUIC connection is established, the client sends its HTTP request using HTTP/3. Security and performance summary. As we conclude this presentation, let's summarize the key security and performance considerations across HTTP versions and the mechanisms that protect them. We've covered a lot of ground, from the evolution of HTTP protocols to security mechanisms like HSTS and protocol negotiation through ALPN. Understanding these concepts together provides a complete picture of modern web security and performance. HTTP/1.1, HTTP/2, and HTTP/3 each represent significant steps in the evolution of web protocols. HTTP/1.1's text-based simplicity made it easy to debug and widely adoptable, but its sequential processing and multiple connection requirements limited performance. HTTP/2 addressed these limitations with binary framing, multiplexing, and header compression, dramatically improving performance for modern web applications. HTTP/3 took the next step by moving to QUIC over UDP, eliminating transport layer head of line blocking and enabling faster connection establishment. Security has evolved alongside performance. HTTPS stripping attacks exploit the transition from HTTP to HTTPS, allowing attackers to downgrade connections and intercept sensitive data. HSTS provides critical protection by telling browsers to always use HTTPS for a domain, preventing downgrade attacks. The HSTS preload list extends this protection to the very first connection, eliminating the trust on first use vulnerability. These security mechanisms are essential for protecting users, especially on untrusted networks like public Wi-Fi. ALPN plays a crucial role in secure protocol negotiation. By integrating protocol selection into the TLS handshake, ALPN ensures that clients and servers agree on HTTP/2 or HTTP/3 securely, preventing protocol downgrade attacks. The negotiation happens early in the connection establishment with minimal overhead, enabling efficient adoption of newer protocols. For HTTP/3, the combination of alt service discovery and ALPN negotiation within QUIC creates a robust deployment path that maintains backward compatibility. When implementing these technologies, several best practices emerge. Deploy HTTPS universally, using valid certificates and automated renewal. Implement HSTS with a staged rollout, beginning with short max age values and gradually increasing them. Consider HSTS preload for high-security applications, but understand the long-term commitment that is involved. Support HTTP/2 on your servers to benefit from multiplexing and header compression. Monitor your traffic to understand protocol adoption and performance impacts. Looking forward, HTTP/3 adoption continues to grow as more servers and clients support QUIC. The protocol's benefits are most noticeable on high latency or lossy networks, making it particularly valuable for mobile users and international connections. As UDP-based protocols become more common and middleboxes adapt, HTTP/3 will likely become the dominant protocol for web communication. Understanding these protocols, their security mechanisms, and their performance characteristics prepares you for the evolving landscape of web technology. Thank you for your attendance. Please consider subscribing to the channel.